In our previous introduction to volumes of solids of revolution video, we used the common disk method, and in this method, in this video, we're going to be looking at the cylindrical shells method. We're going to do a question that we already did in the previous video using the different method, just to explain how it works. But then the second question we're going to do in this video is one where the cylindrical shells method is far more powerful and easy. Okay, so let's just have a look at question 1. Now, in the previous video, the way we answered this is using the disk method. So let's just have a quick look at drawing it. Here's the x-axis, the y-axis. Okay, so we've got the line here, y equals x, and we've got the line here, y equals 2x. Okay, and we're doing it between 0 and 6, so let's put the point down here, x equals 6, and the point here is x equals 0. So clearly this is the area that we're going to rotate around the x-axis, and the way we did it previously was we took this point here and we used a disk. So we had a disk like that, which we rotated all the way around the x-axis, and then we took away this disk, which we rotated around the x-axis to give us a sort of a washer, and we integrated that between x goes from 0 to 6, and basically what that gave us was, using basically this would be pi r squared and this would be pi r squared, we ended up with pi, the integral between 0 and 6 of 2x squared minus x squared dx, a fairly simple integral, which gave us the volume of revolution of this around the x-axis. Now we're going to do exactly the same thing, and by the way, the answer we got was 216 pi, so we better get exactly the same answer using the cylindrical shells method or we're in trouble. Okay, so let's just redraw this, and we're going to do it using the cylindrical shells method, okay, because it's slightly different. So here again is the y-axis, the x-axis, here is the line y equals x, and here is the line y equals 2x, okay, and here is the point x equals 6, and here is the point x equals 0, so let's draw the line down there. So again, this is the region that we are going to rotate around the x-axis, but we're going to do it slightly differently. Now just let's now if y equals 2x, and that's the point x equals 6, then this is the point 12. Okay, this time what we're going to do is we are going to get a little shell here, which is width of dy this time, and what we're going to be doing is we are going to be integrating between y equals 0 and y equals 12, even though we're going to go around the x-axis. And what we're going to do is we're going to take this shell and we are going to rotate that shell all the way round the x-axis like that, and the area, the volume of that little cylindrical shell is going to be basically the height of the shell, which is that bit, times by the radius around what we are integrating, so the radius around what we're rotating, sorry, times by dy, and then we were going to integrate all of that. Now in this particular example, we need to split because we have this line here, y equals 6, and then we have the line y equals x. So what we're going to have to do is we're going to have to do it as two separate integrals, and let's go. So what we're going to do is we're going to do it between here, which is between 0 and 6. Okay, so what we're going to do is we are going to take any point, any cylindrical shell here. Okay, now this is the radius, which clearly is y, so that's going to be the integral. We're going to integrate between 0 and 6 here, so that's going to be 2 pi, times 2 pi, obviously times 2 pi. So 2 pi times by the radius, which is y, that's the radius, okay, times by the height. Okay, now the height is going to be that point there, which is, let's call it x1, minus this point here, which is x2, and as y equals 2x, then we have that x equals y over 2. Y equals x obviously means x equals y. So the height of this thing here will be x1 minus x2, which in terms of y is going to be y minus y over 2 dy. That there is the height. And the reason, by the way, that we multiply it by 2y is if you imagine this thing rotated around there, and then we sort of spread it out like that, where this, I'm probably not drawing this very well, but that width there is dx, and basically this length here is going to be 2 pi times the radius, which is basically the circumference of the thing, and then this here is the height. And so basically that's how we can work out the volume of the cylindrical shell, and then all we've got to do is integrate all of the volumes. Okay, so basically doing this one here, that equals 2 pi times the integral between 0 and 6 of y squared over 2 dy, which equals pi times y cubed over 3 between 0 and 6, which is 72 pi. Okay, so we've got the integral of the first bit here, and now we need to do exactly the same, but for the second bit. Now, I'm just going to, let's just quickly redraw it. So basically here's the line y equals x, here is the line y equals x squared, and we are interested now in this bit from 6 up to 12, and it's just because we just want to do the height here. So this time we're now going to be the height here, well that is the point 6, and again this point here is y over 2, so the height is going to be 6 minus y over 2. So when we're integrating between 6 and 12, it's going to be, the volume is going to be 2 pi times the integral between 6 and 12, y again, which is the radius because we're revolving around the x-axis, remember, times by 6 minus y over 2, which is the height, dy. Okay, and that equals 2 pi times the integral between 6 and 12 of 6y minus y squared over 2 dy, which equals 2 pi 3y squared minus y cubed over 6 between 6 and 12, and just a little bit of messing around there, that is equal to 2 pi 432 take away 288 take away 108 take away 36, which equals 144 pi. So that means the volume of this bit when we rotated it around is 144 pi, and the volume of this bit when we rotate it around is 72 pi, and therefore we have that 144 pi plus 72 pi equals 216 pi, which gives us the same answer as we got in the previous video. Now you may be wondering, well, what is the point? Because in actual fact the previous method using the disc is far easier, and it's true, it is easier, and that's why it's worth knowing both methods, because sometimes the disc method is far easier and sometimes the cylindrical shells method is far easier, and question 2 is an example where the cylindrical shells method is far easier. So let's have a look at question 2. What's the volume of the solid obtained by revolving the region bounded by y equals 2x(z1), y equals 3, x equals 4 about the line y equals 10? Now this is the bit that makes it complicated, because we're not revolving around the x or the y axis. So if we were going to use the disc method, we have to do all sorts of translations and messing around. But with the cylindrical shells method, it's quite simple. So let's just have a quick look at what it is that we are integrating. So we have the line here, y equals 2x. So clearly this point here is 0, 1. And then the line y equals 3. Here's the line y equals 3. And then the line x equals 4. Here's the line x equals 4. Which means that that point there is clearly going to be 9, 4. 4, 9. That point there is 4, 9, and we are revolving around the line y equals 10. So we're going to revolve it around this line here, y equals 10. So we are revolving this around that. Okay, so basically with the cylindrical shells method, this is actually quite simple. So what we're going to do is we're going to do our cylindrical shell again. Here is our cylindrical shell, any old cylindrical shell there, which has a height of dy, and we are going to be integrating between this point here, which is y equals 3, and this point here, which is y equals 9, and we are going to be integrating that around this line y equals 10. And the only complicated bit about this is what is that radius and what is the height. Okay, so let's just have a look at those one at a time. So the radius, i.e. the distance of the cylindrical shell from the from the axis of revolution. The radius is going to be equal, but we know that point is 10, and we know this height here is, y. So this radius here is simply 10 minus y. So that's the radius is 10 minus y. And now we just got to get the height. Well, we know this point here is 4, and we know this point here is going, well, if y equals 2x plus 1, then x equals y minus 1 over 2. So this point here, let's call it x1. So the height will be equal to 4 minus x1. So the height will equal 4 minus y minus 1 over 2. So now we have all of our constituent parts, and all we need to do to find the volume now is the volume equals 2 pi times the integral between 3 and 9 here of the radius, which we just established is 10 minus y, times the height, which is 4 minus y minus 1 over 2 dy. And that is basically all we need to do. We don't need to do any translations or anything. So that equals pi times the integral between 3 and 9, just tidying this up, 10 minus y, 9 minus y dy. And that equals pi times the integral between 3 and 9 of 90 minus 19y add y squared dy. Now it's just a simple matter of working out this definite integral, which is equal to pi times by 90y minus 19y squared over 2 add y cubed over 3 between 3 and 9, which is pi times, it's just a little bit tricky, this 19 times 81 over 2, 243 minus 270 minus 19 times 9 over 2, add 9, which equals pi times 774 minus 19 times 72 over 2, which is pi times 774 minus 684, which finally gives us our answer, 90 pi. So the volume is 90 pi. And you can see this is a very, very powerful method when we are looking to find volumes of revolution about axes which are not either the x-axis or the y-axis, because basically all you need to do is make a very tiny amendment to the general way that you do the cylindrical shells method, just to adjust for a slightly different radius. Okay, well, I hope you found this useful. If you have, please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.